In the forefront of directed energy advancements, Israel's Rafael Advanced Defense Systems has pioneered the Ironbeam high-energy laser weapon system, a 100-kilowatt class platform that redefines aerial interception through instantaneous, precision energy delivery. This fiber laser-based effector generates a coherent beam by amplifying light through rare earth-doped optical fibers, achieving power levels that exceed tens of kilowatts per module, with coherent combination scaling to the full output. The system's 450mm aperture in its latest Ironbeam 450 variant allows for tighter beam focus, enabling energy densities capable of ablating metallic surfaces at distances up to 10 kilometers. By employing hundreds of small, coin-sized subbeams that converge on a target, it mitigates atmospheric dispersion, where air molecules scatter larger beams, ensuring cumulative energy buildup for rapid neutralization. This approach contrasts with traditional kinetic interceptors, as the Ironbeam operates silently, with no projectile trajectory, and its effects are confined to thermal disruption, vaporizing materials or detonating payloads without explosive debris. The laser generation process begins with a master oscillator, a low-power seed laser that produces a stable, narrow line-width signal at approximately 1 micrometer wavelength, optimized for minimal absorption by atmospheric water vapor and carbon dioxide. This signal is split into multiple amplification channels, each consisting of fiber coils pumped by high-efficiency diode lasers, which stimulate emission through population inversion in ytterbium ions. Amplification boosts power while preserving beam quality, measured by an m-squared factor below 1.5, indicating near-diffraction limited performance. Coherent beam combination then reunites these amplified beams using phase-locking techniques, such as diffractive optical elements or active feedback loops with piezoelectric phase modulators, ensuring in-phase interference that multiplies intensity without increasing divergence. The resulting beam exits through a beam director with a 450mm primary mirror, coded for high reflectivity in the infrared spectrum, and is steered by high-precision gimbals driven by brushless DC motors for sub-milliradian accuracy. Atmospheric compensation is integral, addressing challenges like thermal blooming, where the beam heats air pockets, causing refractive index changes that defocus energy. The system deploys a low-power diagnostic laser to probe the propagation path, measuring wavefront distortions via Shack-Hartmann sensors that divide the incoming light into subapertures for phase analysis. Data feeds into a deformable mirror array, comprising hundreds of microactuators that adjust surface curvature at kilohertz rates, restoring beam coherence with Strehl ratios above 0.8, meaning over 80% of ideal focus is maintained. For turbulent conditions, adaptive algorithms incorporate predictive modeling based on Kolmogorov turbulence theory, anticipating scintillation effects and pre-correcting the beam profile from Gaussian to flat-top distributions using spatial light modulators. This ensures effective energy delivery even in light dust or humidity, though performance degrades in dense fog due to my scattering, where particles comparable to the wavelength diffuse the beam. Detection and tracking form the procedural foundation, initiated by a multifunction phased array radar with gallium nitride transmitreceive modules, scanning 360 degrees with electronic beam steering for rapid volume search. Operating in X-band frequencies for high resolution, it employs pulse Doppler processing to filter clutter and compute target kinematics, including range, velocity, and azimuth with meter-level precision. Upon detection, an electro-optical suite engages, featuring cooled mercury-cadmium telluride infrared detectors for thermal imaging, capable of resolving heat signatures from drone engines at 15 kilometers. A visible zoom camera with narrow field-of-view optics provides detailed visual confirmation, while a laser rangefinder emits ISAFE 1.5 micrometer pulses, using time-of-flight measurements for centimeter-accurate distance. Sensor fusion occurs in a central processing unit running Kalman filters, which integrate noisy data streams to predict trajectories, accounting for wind drag and gravitational drop through differential equations. Once a threat is acquired, such as a quadcopter drone at 5 kilometers, the command and control software, hosted on ruggedized servers with redundant power supplies, evaluates intent using machine learning classifiers trained on historical datasets of rocket and UAV behaviors. If hostile, the beam director slews via inertial navigation-assisted gimbals, aligning the optical axis within milliseconds. Pre-fire calibration involves firing a low-energy pulse to sample atmospheric conditions, adjusting adaptive optics accordingly. Engagement commences with the high-energy beam, modulated in continuous wave mode for sustained heating or pulsed mode for shock-induced fractures, delivering energy fluxes exceeding 10 kilowatts per square centimeter. The beam targets specific vulnerabilities. For drones, it focuses on lithium polymer batteries, causing thermal runaway through rapid heating to 700 degrees Celsius, leading to electrolyte vaporization and explosion. Against rockets, it penetrates thin-skinned casings to ignite solid propellants, exploiting hypergolic reactions for mid-flight detonation. Real-time monitoring uses backscatter analysis from the thermal camera, detecting temperature spikes via blackbody radiation curves, and adjusts power output dynamically through feedback loops to minimize dwell time, typically 2 to 4 seconds for small UAVs. For swarm threats, the system employs rapid retargeting, prioritizing via graph-based algorithms that model group dynamics as connected nodes, sequencing engagements to disrupt formations. Post-neutralization, fragmentation is tracked to ensure no secondary hazards, with data logged for after-action review, including beam efficiency metrics like wall plug efficiency, which measures electrical to optical conversion at over 30%. Safety protocols integrate identification friend or foe transponders and geofenced no-fire zones, halting a mission if paths intersect allied assets. The cycle resets automatically, with cooling systems, using heat pipes and liquid nitrogen circulators, dissipating amplifier waste heat to prevent thermal lensing in the fibers. India's advancements in this arena feature the Defense Research and Development Organization's 30-kilowatt directed energy weapon, a solid-state laser platform that converges 6 5-kilowatt modules into a unified beam via prism-based combiners, achieving focused intensities for targets beyond 3 kilometers. Utilizing neodymium-doped yttrium aluminum garnet crystals pumped by diode arrays, it operates at 1.06 micrometers, with frequency doubling for enhanced atmospheric penetration. Power storage relies on high-voltage capacitors, enabling burst operations from mobile vehicles, while vibration isolation through active dampers ensures stability in terrains like the Himalayas. Detection mirrors Israel's with active electronically scanned arrays for initial cues, transitioning to focal plane array infrared trackers that employ centroid algorithms for sub-pixel accuracy. Tracking incorporates particle filters to handle nonlinear drone maneuvers, predicting paths via Monte Carlo sampling of possible states. The beam director, equipped with piezoelectric tip-tilt mirrors, corrects for platform motion at microsecond intervals. Firing sequences use pulse width modulation, tailoring duty cycles to deposit energy precisely, such as overheating drone circuit boards to induce dielectric breakdown. Tests in 2025 validated swarm countermeasures, where the system blinded electro-optical sensors by overwhelming photodiodes with photon flux, or severed carbon fiber frames through pyrolytic decomposition. Scaling efforts target 100 kilowatt thresholds using Raman amplification, where stimulated scattering in silica fibers shifts wavelengths to reduce losses. Integration with India's counter-UAS grid adds layered defense, combining soft electronic attacks with hard thermal kills. These technologies elevate modern drone warfare by addressing the exponential growth of unmanned threats, which leverage commercial off-the-shelf components for asymmetric advantages. Drones, often costing under $1,000, can swarm in formations exceeding 100 units, saturating radar with false positives and depleting kinetic munitions priced at $50,000 per shot. Lasers counter this with unlimited capacity, drawing solely from electrical generators, and per intercept costs of $2 to $5, factoring electricity and negligible wear. Their propagation at light speed, 300,000 kilometers per second, negates evasion, as targets cannot react before impact, unlike missiles with finite acceleration. Beam tunability allows non-lethal options, such as dazzling optical payloads via coherent light interference or lethal ablation, minimizing fallout in urban environments. In swarm dynamics, lasers excel through sequential targeting, using optimization algorithms like greedy heuristics to select high-threat nodes first, disrupting collective behaviors modeled by flocking equations. This thwarts decoy strategies, where inexpensive units mask kamikaze variants. Spectral analysis distinguishes thermal profiles, prioritizing armed drones. Silent operation denies auditory cues, while invisibility in infrared spectra enhances surprise, contrasting audible missile launches. Weather resilience, via adaptive corrections, extends utility over jamming systems vulnerable to frequency hopping. Operation Sindoor, spanning May 5 to 8, 2025, crystallized these imperatives in a South Asian context. Broader implications include deterrence shifts. Lasers raise entry barriers for drone aggression, forcing adversaries to develop hardened designs with ceramic ablatives or frequency-agile evasion. In algorithmic terms, they enhance battlespace AI, providing real-time data for neural networks training on engagement patterns. Post-Sindoor, India prioritized laser inductions, recognizing their role in hybrid threats blending drones with cyber intrusions. Israel's export policy, announced in 2025, facilitates technology transfer to allies, including modular kits for naval variants with stabilized turrets for sea states up to Force 5. This could involve joint ventures, merging Rafael's phase locking with Bayer innovations in power storage, fostering interoperability in coalitions facing Houthi-style drone barrages. Exports include simulation suites using virtual reality for operator training, replicating scenarios like Sindoor's swarm densities. Further technical expansion on Ironbeam reveals its multi-channel transmitter, with separate paths for HEL delivery, tracking, and illumination. The laser illuminator uses frequency-doubled beams at 532 nanometers for visible designation, aiding joint forces. Telecommunications employ free space optics for jam-resistant links, transmitting data at gigabit rates via modulated lasers. Against advanced countermeasures, like drone-mounted mirrors, the system shifts to pulsed modes, inducing vibrational resonances that shatter coatings. India's platform incorporates similar versatility, with plans for airborne mounts using gyro-stabilized pods, extending ranges to 20 kilometers from high altitudes. Its software uses deep learning for anomaly detection, identifying stealth drones via subtle atmospheric disturbances. In drone warfare evolution, lasers address miniaturization trends, where nano-UAVs evade nets. Focused beams target microelectronics, causing avalanche breakdowns in semiconductors. Sindoor's autonomy emphasis previews this, with lasers providing ethical hardkill options compliant with Geneva protocols. Global dissemination via exports could standardize defenses, as with Iron Dome, but risks proliferation of countermeasures. Nonetheless, they promise economical shields against escalating threats. Elaborating on beam physics, the iron beam's output follows the laser rate equations, balancing gain and loss for steady-state oscillation, with quantum efficiency over 70% in fiber amplifiers. Pulse shaping via acousto-optic modulators creates tailored waveforms, optimizing for material-specific absorption. For India's system, crystal cooling uses thermoelectric modules, maintaining rod temperatures below 50 degrees Celsius to prevent thermal lensing. Testing metrics show 95% hit rates against maneuvering targets at 2 kilometers, with energy per kill under 10 megajoules. Sindoor's tactical innovations, like Pakistan's use of balloon-launch decoys, highlight laser advantages in volume discrimination, using Doppler LiDAR FO. Our velocity-based filtering. Exports may include scaled variants, like the 50-kilowatt Ironbeam M for trucks, with 250mm apertures for rapid deployment. This modular family adapts to diverse theaters, from desert to maritime. In conclusion, these systems embody a paradigm of energy dominance, transforming conflicts like Sindoor into domains of precision and sustainability.